Hi, welcome to the Penguin Post newspaper by kids. Today we are interviewing Dr. Richard Bykowski. He's a paleontologist working at Georgia State University. Let's ask him some questions.
Can you tell us about what you study and explore?
Yeah, so I'm a paleontologist. I do specialize on dinosaurs, but I'm also very interested in other animals with backbones, so other vertebrates. More specifically, I consider myself a paleoecologist. And what that means is I'm interested in understanding how different animals, dinosaurs in this case, coexist and interact. So for example, this is a replica of a T-Rex tooth, and you can see it's, kind of banana shaped. This is a tooth, another replica of an animal like T-Rex. It's called Carcharodontosaurus. It's about the same size, and if you notice immediately, its tooth is very, very flat. So one question that would be interested in is, why would two big meat-eating dinosaurs, have two drastically different teeth? Why was T-Rex so, spiky and banana-like in its teeth, and why was something like Carcharodontosaurus a lot like, like a knife? And those are questions that go beyond, here's a cool fossil. The questions I like to ask are, why did they have different teeth? Did it mean that they were eating different things? Did it mean that they were using them in a different way? So questions like that are ones that, I usually answer. So I'm not someone that's going to go out and find fossils every year and then be like, hey, I found this. I'm someone that's going to go out and say, like, cool fossil. Let me see how it actually lived.
How did you become interested in dinosaurs that don't fly?
That's a really good question. I guess it probably started about when I was mostly your ages. I really got into dinosaurs as a kid, and I started learning a lot about them. And the more I learned, the more questions, I had. And the more questions I had, the more I tried to learn. And the more I learned, it was a cycle like that where I kept asking questions and learning more. And then one day I realized, hey, I could do this when I grow up. And once I realized that, I decided that I was going to be a paleontologist. And it really came from, being really curious as a kid and, seeing all the museum exhibits and seeing all the folks on TV digging stuff up, and seeing that, the study of dinosaurs is something that people do. And it became this real kind of lifelong thing that, I was very fortunate and happy to be able to do.
What would you tell kids our age that would get them excited about paleontology? What should they do to prepare?
That's a really good question too. I think the first thing I'd probably tell you guys is you don't need to, be a scientist to be a paleontologist. You don't need to be into science necessarily. You got to like it a little bit, but there are folks who are paleontologists today that do art. All the wonderful images, if you go online and you search for, dinosaur pictures, you'll find artists who are designing stuff online. A lot of them have gone to school to be a paleontologist, but they didn't want to do the science side of things. They wanted to do the art side of things. If you are interested in computers, if you like math, that is getting to be a very big area in paleontology. So paleontology is no longer just limited to going out and digging up fossils, although that's, the fun part of it. But one of the cool things that we can do is we can pull from many, many different areas. I said you can pull from art, from computers, from math. If you like chemistry instead of biology, there are folks that are using chemicals to study fossils. There are folks that are interested in the history of the study of fossils. So understanding what paleontologists were thinking 100 years ago versus what we're thinking today, and kind of how those ideas changed over time. So I think that's one really cool, some exciting things about paleontology, that you just don't have to go do the things you'd expect. And the second, and what was the second half of that?
What should they do to prepare?
But if you are interested, I would recommend, thinking about, do you like being outside or inside? So if you're someone that likes being outside and playing in the dirt, you probably want to go study geology, which is the study of rocks and the history of the earth. You can learn about fossils and rocks and how to go about, being outdoors and digging stuff up. If you like being indoors, you can go the biology side and you can study animals. You can do a lot of dissections, learning about how animals are put together. That's really cool. Also, and I know a lot of students, don't like this, you got to know math. I use a lot of math when I do research. Understanding how you can take measurements and do calculations tells you a lot about ancient ecosystems and ancient animals. So you got to study biology, you got to study geology, and you got to study math.
What is your favorite vertebrate fossil?
That's a really good question. I'm actually going to show you a picture of it. Can you guys see the image on the screen?
Yeah.
Yeah. So this is probably my favorite fossil. So a couple of years ago, I was on a field trip up here in Alberta. So there's the museum. That's the Royal Tyrrell Museum. It's a great place if you're interested in dinosaurs. Might be the best dinosaur museum in the world. But I was out on a field trip near the museum with some other folks, and we were looking at some hillsides. And I just happened to look down, and I saw this little fossil here, about that big, okay? And what's cool about it is this is a piece of rib. So if you kind of feel along your sides here, that's a rib bone of a dinosaur. But what's actually really cool about it is these two lines right here, those perfectly parallel lines, those are bite marks. This rib here was probably from a duck-billed dinosaur, something like this, who had a really, really bad day. And what I think happened was this little fossil here was snacked on by something like a T-Rex or one of its relatives. And what's cool about it is the little bite marks here actually preserve evidence of two dinosaurs interacting with one another. And it's a really cool little fossil. Unfortunately, I wasn't able to keep it, so I put it back, literally right back there on the ground where I took the picture. So hopefully someone else can come along and see it and get the same experience. Or folks from the museum that I was with came back and picked it up and put it in a collection space. But it's a really cool little fossil that tells a really awesome story.
Where do you go to find fossils?
Another good question. Most dinosaur fossils in the United States and Canada in particular are found in this area. So this area where I'm kind of circling right here. If you are living if you're living somewhere like I am in Georgia, there actually aren't a lot of dinosaur fossils here. And the reason because of it is there are no rocks that date to the age of dinosaurs in Georgia, or they're very, very rare. If you want to find fossils, any fossils, you need a couple of things. One, you need a specific type of rock. You need a sedimentary rock. These are things like sandstones and limestones and shales, things that get deposited by running water quite often. So you need sedimentary rock. The second thing you need is sedimentary rock that is of the right age. So if I wanted to go find a fossil of a T-Rex, I need sedimentary rocks that date to the late Cretaceous, about 67 million years ago, or 66 million years ago, in that range. If the rocks are too old, you're not going to find a T-Rex in them. If they're too young, you also won't find a T-Rex in them. And probably the third thing you need with those rocks, and this is probably most important, you need rocks exposed at the surface. You need to be able to see them. There are places in the world where, yes, there are rocks that, contain dinosaur fossils, but they're buried so deep underground that no one has the time, the energy, or the resources to go get them. A lot of paleontology involves finding fossils in rocks that you can see the rocks. And like I mentioned, here in Georgia, rocks that date to the Mesozoic just aren't found very commonly on the surface. You go somewhere out west like Colorado, Montana, Wyoming, South Dakota, and those rocks are just sitting out there for you just to go put your hand on. So if you know all that, you can find dinosaur fossils or any fossils. You just have to fit the right criteria.
What does your day look like when you're out digging for fossils?
That's another really good question. And I'm going to go ahead and kind of share some images of what my day actually looks like. So contrary to everything else, I actually don't go dig up a lot of fossils. I am a paleontologist, as you can see from the images here. I do most of my work going to museums. So this is an image over here of me at the Natural History Museum in Utah looking at some of their carnivorous dinosaurs. This is me at a museum in Illinois looking at horned dinosaurs, like this is actually Triceratops. This is the skull bone of a T-Rex relative called Daspletosaurus. And part of the reason I don't go looking for fossils is what I said a few minutes ago. In Georgia, there aren't a lot of dinosaur fossils. They're very, very rare. So for the questions that I like to do research on, I like to go to museums and look at stuff that other folks have collected. And the reason I do that is sometimes you go out looking for fossils, you come back empty-handed. You actually come back empty-handed quite often. And if you go to a museum, you're guaranteed to find a fossil that you need. And for someone like me, all I need to do to go to a museum is call up the curator, tell them who I am, what I want to come see, and they're gonna, I can go make an appointment. They're gonna let me in the special back room where all the fossils are kept. So a typical day for me when I'm doing research involves going to a museum, right after breakfast. I might bring my orange juice and a donut with me. Might bring a tape measure, a camera, a notebook. I like taking written notes. I lay it all out on a table and I start opening drawers and pulling out bones, and I start measuring them and taking photos of them. And I think it's a lot of fun because sometimes, as you can kind of see in this picture, I'm right on the exhibit. So when I was taking this photo, and the curator who was assisting me took the photo of me taking a photo, there were people walking around looking at the exhibits. So I'm pretty sure I made it into someone's vacation photos, which is pretty cool. But it just goes to show you that a lot of paleontologists don't necessarily go dig up fossils. And the other reason we don't it's cold. The field season is basically May, June, July, August, and September. And if you can't get fossils in that time, you really don't want to go to places like Montana in December or January where it's going to be really cold and snowy. So given the limited amount of time and, during that time of the year, I'm also a teacher. So I teach here at Georgia State University. Classes are in session. So I can't really go out to the field other than when I'm on summer break. But museum trips, that's where I get all my data from.
Who is your favorite paleontologist?
My favorite paleontologist? That's a good question too. I would probably have to say a paleontologist by the name of Dr. Phil Curry from the University of Alberta. I was about 4 or 5 years old, and I had watched so many dinosaur documentaries on TV that I knew Dr. Curry by sight, by voice. I'd seen him speak in all these TV shows. And one day, he was actually visiting my hometown, the Natural History Museum in my hometown. That's in Chicago, the Field Museum. And my parents heard about it, and we got tickets to go hear him talk. And there was me, about 4 or 5 years old, sitting in this room with all these professionals and adults and graduate students and people who are much older than me, listening to Dr. Curry talk. And I think what struck me afterwards was, according to my mom, after his talk was over, we got up to leave, and instead of walking out the door, I walked right down to the front stage to go ask him a question. And I was this little 5, 6-year-old kid in a sea of like grown-ups trying to ask him a question, and I finally got up there. I asked him a question, and he ended up signing this little picture that I drew, and then that picture is somewhere, but it's something that really struck me when I was really young, that he took the time to answer my question and talk to me. And that's something that stuck with me for a while, and it's something I've tried to do once I grew up. Just that he was that nice and that willing to like share a few minutes of his time with this little kid that just liked dinosaurs. So I've always felt very grateful for that time.
Can you tell us a little bit about geometric morphometrics?
Geometric morphometrics, that's a mouthful. Oh, here we go. So geometric morphometrics is a research tool that I use. And the image that you see on the screen are jawbones. So this is this part of your mouth. But these are actually jawbones of mice. I didn't actually always do dinosaurs. I did some research on mice. And when you're looking at a bone, you often want to describe its shape. So if I were to ask you guys, look at this image here, and how would you say, how would you describe the shape of that bone to me?
I would say it's like kind of like a wave.
Kind of like a wave. Okay. Anybody else?
It is kind of like a wave. It looks like a bottom jaw.
Yeah. So one thing that we try to do in science is we want to measure what a wave is. So numerically, how can we put numbers on that wave shape? And traditionally, what we do is we take measurements like that. So every one of those colored bars represents, a place where I stuck a tape measure. Now keep in mind, mouse jaws are about that big. So it's a very, very tiny tape measure. With geometric morphometrics, instead of taking measurements with a tape measure, I take measurements with a computer, in that I take points. So if you've ever looked at a map, or if you're familiar with like latitude and longitude, geometric morphometric points work a lot like that. I use a computer, I click on it, and it sets a point right there. And then I move to the next point, and it sets another point. Now, I'm going to take the bottom image, the base images away. Which one of those still looks like the jaw? The geometric morphometric one here in green, or the one where I took measurements here?
The one in green?
Yeah. Yeah, you can see it still looks like that shape. So geometric morphometrics is a great way to take any sort of skeletal part, any bone, any shell, any tooth, and really capture its shape. So when I'm looking at something like this, you see all these funny little shapes here? Imagine, for example, if this point here, number 2, moved this way. Just, on a different specimen, it went this way. What would that do to this shape here? What would happen if points 7 and 8 got closer together? The shapes here would all change a little bit. And for me, that's something that's really useful because I'll show you guys right here. This space right here, this is where one of the mouse's muscles for chewing attach. It's called the masseter muscle. And you've got one too. It helps you close your jaw. And as this kind of square shape changes a little bit, that might tell me something about what's happening with that mouse's jaw muscle, which is really cool because you might predict that if this little critter was eating really hard food and like cracking nuts, it's going to need a much stronger muscle. So this shape here might actually get bigger. Whereas if it was eating soft foods like fruit, it might get smaller. So geometric morphometrics allows me to look at shape, the shape of pretty much anything, and say something about what it does. And some of the research that I'm doing right now, this is a scale replica of a T-Rex skull. So if I really were to have a real one, it would be about 10 times this big. But I'm actually studying this bone right here. This is called the maxilla. And what's cool about the maxilla is this is where all the big teeth are in a dinosaur like T-Rex. So understanding the shape of this bone here can tell me something about, what's going on with T-Rex's skull and maybe what it was doing to eat food. Yeah.
How does the history of dinosaurs change?
Another good question. I'll again put up some images, but what I think is really cool is that these 3 images here represent about 100 years of study of everybody's favorite dinosaur, T-Rex. So T-Rex was first discovered and described in about 1902, so well over 100 years ago. And when it was first described, this image here is what we thought it looked like. Standing straight up, tail, on the ground right behind it, looking very slow, ponderous, maybe a little dull, reptile-like, okay? If we flash forward to around the 1990s, we get the first big release of a very famous movie you might have heard of, Jurassic Park. And as you can see here, T-Rex changed a lot in about the 90 years between its first discovery and Jurassic Park. For one, instead of standing straight up, it's kind of bent over horizontally, and its tail is now up in the air. It became a faster, more intelligent animal based on stuff that we've gathered. And Jurassic Park at this time is almost 30 years old, so that movie's quite old. Now what we understand, and here's another image from a game that's supposed to come out. If you notice about T-Rex, it's covered in feathers. So in about 100 years, we've gone from looking at T-Rex as this kind of dull, upright, lumbering Godzilla thing to something very, very bird-like. And I think that's really awesome to think about because, you know, even when I was your age, this was kind of the default image of T-Rex. I was probably a little bit older than you guys when Jurassic Park came out, and that changed like immediately in my lifetime. And in the last 10 years, 15 years, T-Rexes look more like a giant chicken than Godzilla, which I think is really awesome and shows that science progresses through each incremental discovery.
That was so cool. We learned a lot from you, and thank you for your time. Bye.
All right. Bye, guys. Thanks for having me. Good luck.